Thank you, everyone. I'm happy to be here today, and I hope you enjoy the talk. I have a voice that doesn't carry so well, so if it's at the back and you're not hearing me, just raise your hand or something throughout. And please just ask questions during the lecture, whether you raise your hands or not. And I'm happy to be talking today about LASP in general, solar irradiance at LASP and the International Space Station. This is going to be a new frontier for us. So it's quite an exciting part in the history of LASP and solar irradiance measurements, being just from the International Space Station, but also from improvements primarily in calibration and characterization of spectral irradiance measurements of the sun. I wanted to point out special thanks to a few other members, a couple who are in the audience here tonight. Pat Brown, want to raise your hand? And Eric Richard. Also happy to have Tom Sparn, the TSIS program manager here. Want to raise your hand, Tom? All right. So this is a photograph here. This is taken by a spacewalker, an astronaut, on the International Space Station. This is a few years old, but it's taken roughly from the location of where the future TSIS instruments will be, and it has a view of the sun, and it's just a nice way to set off the lecture. So here's another beautiful view of the International Space Station, and we're going to talk about this more primarily towards the end of the talk. It's always interesting to start off with some basics. What's the motivation for our discussion here today? So just some basics about the sun. I'm going to spend most of the talk talking about our current knowledge in the measurements of total and spectral solar irradiance and modeling. And then I'll lead into the future of solar irradiance, which is really calibration facilities and the TSIS mission. And at the end will be the funnest part, is the International Space Station. Largely some movies of kind of, I guess you call it engineering developed movies, demonstrating some of the technical challenges that have to be met, or that's different from making irradiance measurements from a large structure like this. Okay, so diving into the first section, we look at these images here. These are atmospheric imaging assembly images from the Solar Dynamics Observatory, and they're taken roughly 15 minutes apart on the same region of the sun. And when I look at images like this, my curiosity rises, and I start to wonder things about, what is the structure of the sun? Why does it have these irregular features that are dynamical in origin? How hot is it? What is the temperature change to make some of these regions brighter than others and cooler in other regions? And other questions like, as we see, I'm going to kind of point out here as time is going on, you can see some elements actually departing from the sun. So you can think to yourself, well, what does that impact, or does it have any impact to us on the surface of Earth? So these are some of the questions that when I look at these images, I'd like to know about the sun. So if we move on to the next slide, this is two really cartoon renditions of the layers of the sun, what we know about it. The one on the left actually is kind of this neat superposition of actual measurements over top, an artist rendition. And the one here on the side is just kind of a side view cartoon. And what I'd like to point out here is just the scale. The sun, we know, is very large. And at the center, it has a core. What's interesting about the sun is that despite being a big ball of gas, it actually has an interior and an atmosphere. So right at the very center in the core is very hot region. It's 20 million Kelvin. Actually, the energy is generated by thermonuclear reactions. So temperatures of 20 million Kelvin, and the density there is 160,000 times that of air. So it's extremely dense. As we move out from the core, I'm going to just use this cartoon on the right. It's a little bit easier for me to point. The next layer of the interior of the sun is called the radiation zone, and it's aptly named because the energy transfer through the radiation zone is by photons moving, so radiative. What we find, though, in this zone, it's cooler than the core, quite a bit actually. It's only maybe roughly 7 million Kelvin right there, 2 million right there, and it's still denser than air, much denser than air, but much less dense than the core. However, because of this high density, the photons that start at the base of the radiation zone and are traveling up to the convection zone encounter so many multiple bounces that it can take up to 1 million years for an individual photon of light to make that distance, which is only about 300,000 kilometers. So if it could travel at the speed of light, it would take 1 second to traverse. But because of the high density and the multiple bounces, the transfer of radiation in the radiative zone is extremely slow. Then we come up to the convection zone. This is really what you think of convection. It's actually transferring energy in a different manner. It's by dynamical motions. The transfer of energy is much quicker, and it carries energy from the base up to what we call the solar atmosphere. Temperatures are even lower yet, about 2 million Kelvin. And at the top of the convection zone, which is also the base of what we call the solar atmosphere, or the surface of the sun, it's roughly about 6,000 Kelvin. And at the base of the convection zone, we have still very dense, but by the top, it is only like 1/10,000th the density of air. So quite large changes in temperature and density in the sun. So what we see then on the very outer part of the sun, you can see, let me see if I can point at it right. My pointer is not so, there it goes. Right here, this little slice right there is what we call the photosphere. And if we look on this plot, and that the whole solar atmosphere is this kind of cyan tone, and the photosphere is just that very thin slice at the base of that solar atmosphere. To me, the photosphere is amazing because it is, despite being so small, this is roughly where about 99% of the energy from the sun emits from, is right here in the photosphere. And it's going to be the energy from the photosphere then is the dominant part of my talk today. When we get out to the next layer, the chromosphere, this region that's very irregular, it looks like this bubbling. This is actually, I forgot to mention that there's, in the interior of the sun is a region where they feel magnetic field lines are generated. It's between the radiation zone and the convection zone. And this source of change in these field lines is something called a solar dynamo. And I don't understand that. But what I do understand is that these magnetic elements, these tubes of magnetic loops, can come up through the photosphere into the chromosphere. And that's what we're seeing, really bright regions of rising superheated gas, darker regions where it's relatively cooler. So the chromosphere is very interested. It's more, I guess, more dynamic is what you'd call it. The other thing that's interesting to me about the chromosphere, and that took me a while to get a handle on, is that it's hotter than the photosphere. So, and it kind of is a little bit confusing, because as you're moving away from the core, the source of all this heat, the temperature had been reducing, but all of a sudden, as we go through the chromosphere, it begins to get hotter. And the reason that is that despite that, basically what's happening is that the density is continuing to drop. And so there's fewer particle collisions, less transfer of cooler temperatures through particle collisions. So the temperature is rising. And it continues to rise into the corona here, the outermost layer of the solar atmosphere, where temperatures are risen up to about 1,000,000 Kelvin. So the other things that we can talk about from this plot, oh yeah, one more thing. Because the sun is a ball of gas, it experiences what's called differential rotation. And that basically means that, unlike the Earth, where all parts of the Earth rotate at the same rate, the sun rotates faster at its equator. It takes 27 days for the sun to rotate around at the equator, and about a week longer at the poles. So that's also another interesting feature about the sun. So let's look now again at the photosphere, where I'm going to be concentrating the talk. And I'm going to show a movie here. It's a movie that's actually superimposed from one instrument that is measuring essentially the intensity of the surface of the sun. Excuse me, what we call the surface of the sun, even though it's not solid. And overimposed on that is going to be the total solar irradiance, which is the solar power per unit area integrated over all the wavelengths that's incident at the top of the Earth's atmosphere. And that's measurements made here at LASP, or made here by instruments built at LASP called the Total Irradiance Monitor, that's currently up there measuring on the SORCE satellite. So let's start this movie. And so we can see how the total irradiance varies with these magnetic features that have originated from the core of the sun, have come to the photosphere, and they've erupted in these active regions that to us can have regions of reduced, they're dark, they're actually cooler. The magnetic activity is suppressing the convection up from below, so it's actually regions that are cooler relatively to around it. And so superimposed here is the total solar irradiance. You can see it's varying in time, and as here's a particularly large sunspot group come across, and look at that reduction in the total solar irradiance. That was a 0.34% decrease, and it's kind of returning back to its baseline for this period. And we can swatch it a little bit more here again. I forgot to mention that the time period of this movie is about, forget when it started now, I think it's about 2 solar rotations. To date, actually, this is the largest ever measured decrease in the total solar irradiance in the space era, 0.34% decrease. So what we're seeing is that the magnetic variability from the sun, we're seeing visible manifestations of that magnetic variability as these dark and bright patches on the surface of the sun that is changing the energy output that we receive at Earth. And that magnetic variability has a number of different scales. One of the dominant ones is a 22-year time scale, and that's in the magnetic variability, but we see that as 11-year variability in large amount of spots or active region on the photosphere to a small amount or very minimal. And why that's half is because the magnetic field of the sun flips. So it flips in its polarity. So they call it a 22-year cycle because if it's flipped from one polarity back to the next, it takes a full 22 years. But in the active regions, you see that as 11-year cycle. So that that change over 11-year cycle is about 0.1%. But here we can say on a day-to-day basis, the total solar irradiance can change much more than 0.1%. So let me go to the next slide here. Okay, so I wanted to segue. This is a good way to start to segue into what we currently have about the solar irradiance. I've already introduced some of the measurements of solar irradiance that we're making today. Climate data record is something I'm going to bring up a few times during the talk, so I just wanted to say what I mean when I talk about a climate data record. And I'm also going to then talk more about the total solar irradiance climate data record and the solar spectral irradiance climate data record and contribution by models of TSI as a total solar irradiance and SSI as a solar spectral irradiance. And the image here is the SORCE satellite, launched in 2003 and still making measurements today. Okay. So in brief, a climate data record, if you think about it as a record that's long enough, consistent enough, and has continuity, that you can determine climate variability and change. So as we go through the talk, we're going to talk about the importance of continuous records, high accurate records, and long records. And this is because Earth's climate is something that is changing slowly over long time scales. This is not, it's like the average of weather. So if we want to know how the climate's changed to changes, say, in solar input, we need accurate records that are long enough to deduce this. There's a program developed at NOAA, and I'm not sure exactly what year they started, it's called the Climate Data Record Program. And I just wanted to point out that they've expanded the definition of a climate data record to also include products. Products, the generation of products that have been made using observational records that span these long time periods that are high accurate and continuous. And so here's some of the climate data records that they have developed and are providing through their operation. And I only wanted to mention that in terms of solar irradiance, we're in the unique situation where our measurement is also our product. So we kind of fit hand in hand with both definitions of climate data record. So just to start off the talk, let me move over here a little bit so we can see a little better. This is a really fun thing to peruse on the LASP website if you've been there before. So if you go to the LASP website and you search for, I think it's mission timeline, you'll find that this is a dynamical web page. You can click on any one of these different missions, and it'll take you to a page with more information about it. So I wanted to use it just to kind of bring to context some of the different missions that LASP has been involved with, and introduce some names as I go through the talk. So up here is the sun, and here's the Earth, and so the missions that I'm going to be talking about are kind of in these two categories. So the biggest one I've already mentioned is the SORCE mission with the TIM and SIM, and I should have mentioned SOLSTICE instruments on there. So they're measuring the total irradiance and the spectral irradiance from roughly 100 nanometers up to 2400 nanometers. So the large, about 96% of the energy that's coming from the sun, they're measuring the spectrum of that. So that's a major one that is going to come up in the talk. We have TSIS here, which is the future just TIM and SIM instruments, no SOLSTICE instrument on TSIS. So the SIM has extended, there'll be a 200 nanometer to 2400 nanometer wavelength range for the spectral irradiance measurements from TSIS. And back in time, you can see we have one here I want to mention is the Glory TIM. This was going to be the new accurate total irradiance monitor to launch after SORCE to continue the record from the SORCE TIM. Unfortunately, there was a launch failure, and Glory TIM didn't make orbit. So there was a rough period because there was real concern that this long and continuous and high quality data set that I was talking about was going to have a gap, and that's really detrimental for studies of climate change. So TCTE, or the TSI Calibration Transfer Experiment, was a real success story where they quickly refurbished a SORCE TIM witness unit, recalibrated, and had it launched in, I forget the timeline, it was a year, essentially. Quick. So TCTE TIM is now up there making measurements along with SORCE TIM, and those measurements you'll see later co-line very nicely. There's other important missions up here that have measured solar irradiance, and I'm not going to talk about them so much because they're not measuring in a spectral range that's important for climate. So they cut off around 100 nanometers and below. So those are the extreme ultraviolet measurements, or SDO-EVE, and timed C right here. And then Solar Probe Plus, this is in the future. This is a mission that's going to be measuring the sun's corona, I believe, by essentially flying into it. So quite something. So, oh, I missed one. I'll just mention it in passing. Back here in the 1980s, LASP had the SME Solar Mesosphere Explorer, and that measured ultraviolet up to 400 roughly nanometers. And so that's also another important contribution to our record of solar spectral irradiance. Let's take a look at what the climate data record of total solar irradiance looked like back in 2011, and I'll give a little bit more history for all these missions at the time. So in 2011, the SORCE satellite had been up for about 8 years, and the TIM measurements are shown here in red. And you can see, as you look at this plot, I should point out here first, this is sunspot number at the bottom. So as sunspot numbers are high, this is high solar activity, lots of magnetic features on the photosphere. And this is solar minimum, then maximum, minimum. And you can see this reflected in the total solar irradiance. And the different colors are different total irradiance measurements from other instruments. Some mostly all overlapping somewhat in time. I guess they're all overlapping, but in time, but not in scale. You can see there's a lot of spread between them, and the spread is larger than the total radiance change over a solar cycle. And so people ask, why is this? What is the reason for the spread? It's instrumental. It's just calibration differences. So. But imagine yourself in the footprints of Greg Kopp, who provided this. And at the time, I guess, the most popular wins, and the idea was when SORCE launched that the total solar radiance was, well, you pick a spot in the middle, 1366 watts per square meter. And here comes Tim along down here. And so what I wanted to transition into next is just the importance of a climate data record is just to talk about the legacy of Glory Tim, contributions to a climate data record from an instrument that never flew. So how could this be? Essentially that when they were preparing the next generation total radiance monitor, more higher accurate improved electronics, they wanted a good calibration facility to pin this on the absolute scale. And the Glory Project funded the TSI Radiometer facility that's here at LASP. It's a world-class facility. It's the only facility in the world that can characterize these instruments to 0.01% absolute accuracy at the power levels of the sun and under the vacuum conditions of a space environment. And so this is just an engineering drawing. Essentially what's happening is they use a L1 standards cryogenic radiometer, so it's got the NIST stamp of approval. It's got a transfer calibration to their optical power standard. And there is a very finely calibrated aperture at that cryogenic radiometer. So laser light that enters that is in units of watts per meter square. Then there's a translational stage here that can shift that laser light from the cryogenic radiometer right into this vacuum tank that's holding the TIM radiometer. So they can make a measurement side by side without having to change the laser optics or setup or setting it down a different path. The optics do go through, or the laser light does go through a vacuum window, but that is common to both paths of light, so that's constant, I guess, as you compare these two. So the other thing that I would like to mention is that there is basically the way this calibration facility works, it has this beam steering mirror that can spin this laser light in such a way that it can overfill the aperture of the irradiance instrument in there like the sun would do, or it can underfill it and just be a point pencil beam right through there. And the importance of that is that it looks like I don't have a picture here. The TIM instruments built here at LASP have their precision aperture, basically their per meter, the part that gives a per meter squared to the irradiance measurement, has it out front. So it's got that precision aperture first, and then a view limiting aperture behind. And all the other TSI measurements of all the other instruments had their view limiting aperture out front and their precision one behind. And that was found, it was confirmed in this facility, that these other instruments have erroneous scatter light. So they're overfilled, their view limiting aperture is adding more light into the precision aperture, and their irradiances were measured high. And let's see, so as we look along here, well, here's just what it looks, I call this a sausage making. This is what it really looks like. I mean, I can recognize the cryogenic radiometer, and I can see one of the bellows here, I think. This is the vacuum tank in there, and then I'm lost, you know? So I haven't been able to go in there, so. But this is what we can now see is after this is what I call the legacy of the Glory TIM. Now this plot now goes out to current day. This is updated last March 12, 2015. And we see that there's a collection of measurements that are lying nearly on top of each other from different instruments. And that's essentially the Primos instrument had come here to LASP, was calibrated in the TRF, confirmed that it had extra scattered light. TCTE is the transfer calibration, or TSI calibration transfer experiment, and it was, of course, calibrated here as well, and launched on a ball satellite, actually, ball built, and it confirms very nicely. We also had the Acrim 3 here in green. They were able to improve their calibrations. And then there's another one here, Virgo, and it also visited here. I'm not sure if I quite have the story right. I think they're attributing their calibration change to something else, some other information they had from elsewhere. Nonetheless, it's reduced as well. So all of a sudden, we have this great success story where these continuous and records are longer, they're more accurate, and we're making improvement. So, okay, so I wanted to draw this all together of why solar irradiance is important to the Earth. And this is a cartoon representation, but it's got some numbers on it that are fairly important and are derived from measurements and models. But what you'd have here is incoming solar top of atmosphere irradiance. The number looks different. This is a global average, so it's 1361 divided by 4. And the numbers in the parentheses are the error bars. So the error bars there are small. And if we're in radiation balance, if our climate system is stable, say, then this number is going to be balanced by the two outgoing, the reflected solar and the thermal emission. And if we look here on the bottom, my pointer isn't working so good. Here it is. This 0.6, we're out of balance by 0.6 watts per meter squared, but the uncertainties in that imbalance are roughly the same order of magnitude. So, excuse me, what I wanted to emphasize is that if we think about the total solar radiance measurements that we have, and we look at these imbalances, we see that this imbalance is roughly like I think I get the number here, about 0.1% of the incoming energy or the total outgoing. So we have an idea of what order with the imbalance we have. So if we wanted to, we could define, and this is what we've done, we can know then how good do we have to make our measurement of the total solar radiance coming in to reduce our uncertainties in this imbalance. And the accuracy of the best irradiance measurements today made by SORCE TIM contribute roughly 40% to the uncertainty in the imbalance. And so where we're going with the future irradiance measurements, which are going to be about 3 times more accurate on just a rough scale than the source TIM measurements today, is that we can then reduce the uncertainty in this imbalance to 1/10 of 10% of its mean. So, which means that we can measure to 0.05, our contributions from here, we can reduce that uncertainty to 0.05 watts per meter squared. And that, if you want the numbers, requires an accuracy in the total solar radiance coming in at 100 part per million. And that's our goal for the TSIS TSI. So one of our future stories for our future measurements is reducing the uncertainty in the total solar radiance, so we get a better handle on what is our uncertainty in the imbalance in our energy budget. This doesn't say anything at all about this work here to make these measurements more accurate in the outgoing. So, yeah, we're making the most accurate measurements in this cartoon come from us, and but we at least know what we can do to reduce our source of uncertainties to this. I guess that's my point. But good point. These folks here in the reflected top of atmosphere and the thermal outgoing have some larger uncertainties of their own that they need to tackle. So this is a great segue to begin the talking about the spectral radiance, because as we look down and we come down into the atmosphere, we see that the solar radiation is absorbed in the atmosphere, it's scattered, some reaches down to the surface, about 30% is absorbed at the surface. And I'm going to focus just on the left-hand side of this plot, but what we then know is that, I need a little bit of water. So if we look at what these processes look like, and these values are largely obtained by combinations of measurements and models, radiative transfer modeling. So we know that the Earth responds distinctly to the sun's energy in different wavelength regions, and we can look at this in this kind of 4-point graphic here. If we start in the bottom left, the red curve is the solar radiance at the top of the atmosphere, and the blue curve is what it looks like at the surface. And there's a lot of reductions in absorption features, primarily water vapor, some carbon dioxide, oxygen. If you look up here, this is what's going on in the atmosphere, and I'm not even showing clouds in here, but the black line is the total atmospheric extinction from the molecular scattering and absorption contributions, and there's an aerosol model in here as well. And you can see that the wavelength-dependent sensitivities to the solar radiance have dependencies by source that's also overlapping spectrally. So hard to untangle all this. And then this radiation that's been absorbed and scattered in the atmosphere is going to reach a surface at some point. It could be a cloud, or it could be vegetation or sea ice. And those surfaces have their own properties. And we can see some distinct differences here: water, green vegetation, cloud. So that, and then after reaching a surface, there's going to undergo some further interactions with the atmosphere. Ultimately, it's going to exit the top of the atmosphere as reflected radiation, and it's going to be a mixture. The reflected radiation is going to be a mixture of all these processes that have been going on within the atmosphere. So when we look then at climate data records of solar spectral radiance that we require to understand how this energy is deposited within Earth's atmosphere, and this energy is used as a source for temperature and chemical properties within the atmosphere that sets up the dynamical motions that we need as our weather to live on the average, which is our climate. So in solar spectral radiance, it's a little bit hard to interpret this plot, but what we're seeing as a function of time and as a function of wavelength, and these are our different major missions, we're seeing increasing, if you will, if you could say just a basic trend from these discrete missions that were largely making measurements at wavelengths where this would be more like space weather, not as important for climate. And as we go further in time, we see we're getting the whole spectrum, or at least parts of the spectrum, and kind of more contiguous in time. So we're beginning to develop a climate data record of solar spectral radiance, and I'll point out a few majors here. Here's SORCE. This is a combination of solstice and SIM measurements to cover this whole range. And it's still going today. ISS here is this is the International Space Station, but it's a European group of measurements, and they're not measuring continuously. Essentially, actually, I think they largely have obstructions from the International Space Station, so they can't view as often as they'd like. Here's time C measurements. Back here was that SME data set here, and then if we could tie back in there, but we do have a measurement gap right here. So anyways, it's not as perfect as the TSI, but it's extremely important. We need the spectral irradiance to understand, to attribute climate change to changing drivers within Earth's atmosphere. We need the total irradiance to kind of put a cap on what's coming in, to bound it, but we need the spectral irradiance knowledge to actually do any attribution studies. So this is what the spectrum of solar irradiance looks like, from 200 nanometers to 2400 nanometers. And we see here now it's a solar power per unit area per unit wavelength incident at the top of the atmosphere. And the integral of the spectrum over these wavelengths is roughly 96% of the total solar radiance that the SORCE TIM is measuring right now. And you can see that I just want to point out, it's largely smooth on this side. It's got a lot of structure down here. That's absorption features that are attributed to different elements of the sun, and they're called Fraunhofer lines. And can't remember the first name of the fellow, but it's named after the physicist who originally measured these features. Now let's take a look at what we've learned about how the sun varies over a solar rotation, so that 27-day solar rotation from SORCE, SIM, and solstice. And what I'm showing here on the right is a period of time. This is an image of the photosphere with some active features, and here's looking more in the magnetic. You can see in the region of these active features, you can see stronger magnetic fields and weaker magnetic fields. And this is compared to time roughly 2 weeks later, when there was no really, or maybe there's some small thing there, but relatively quiescent looking surface of the sun. But even in the magnetic field, a lack of visible sunspots and bright features still has magnetic activity. Just wanted to point that out. And for this time period, if you look at the relative difference or the ratio of the active to the quiescent period, we'd see the reduction in the total irradiance due to the blocking of irradiance from the dark feature. And we can look then in the spectrum. And what we're seeing here in the gray is the SORCE. This is actually just SORCE SIM measurements. And the red is a solar variability model. And we see similarities and differences, both of which have been very interesting for us to learn. For example, the bottom plot here is just a blow up of the region from roughly 240 to 400 nanometers. You see in this region of the spectrum, it's more and more clear that the irradiance variability models aren't capturing the level of variability that is actually truly there. And this is actually an instrumental artifact from the SORCE SIM. It's just a deficiency, I'd really call it, in the electronic capability to really discriminate how to say it best. They call it bit noise. So you're measuring irradiance at a certain level, but you can't quite discriminate a small enough change, so you flip to another bit and back, so it's quite noisy. TSIS SIM, these electronics have been improved, and I think the electronic detection capability of TSIS SIM is about 50 times better than that of SORCE SIM. So that's one element that's improving the accuracy of the future irradiance measurements that I'll talk about. Okay. here we go, is we're now looking at over the solar cycle. So this is the roughly 11 years from, well, we're looking at from solar maximum 2002 to solar minimum in 2008. And we're seeing that some of the challenges to measure the solar variability over the solar cycle, we need to not only measure 5 orders of magnitude difference, and the SIM is a prism, so it's got one optical element. So that is one technical challenge in measuring the sun over long time periods. The other technical challenge is that we have to be able to measure changes in this variability, which requires long-term stability in the instrument. And that's another technical challenge that also requires science data analysis and some assumptions and modeling to correct for long-term instrument changes. So I'm going to move ahead here and just briefly talk about the models of solar radiance variability. And just to recap, we know that the sun has periodic behavior, has variability on 11-year time scale and shorter on the rotation. And so if we were wanting to model this, and say if we looked at the sun here and we wanted to say, can we model the irradiance from the sun? We need to know things like the sunspots that alter the energy from the background. Well, first, what is the background energy? How much do these magnetic features change? And can we measure these features, or can we have proxies for them? So I'm just going to mention in brief that this actually solar radiance modeling is something that we're doing here at LASP with Judith Lean at the Naval Research Lab. And we're using a proxy model, and based on the SORCE measurements for the last decade, SORCE TIM and SIM measurements, solstice. And we've basically derived relationships between the measured irradiance from the SORCE satellite and proxy indices. For facular brightening, we use the magnesium-2 index, which is a measure of the chromospheric variability in the sun. And then we use records of sunspot area and location to determine how much sunspots are on the solar disk at any particular time. So we know what our background spectrum is from SORCE. And if you can see, the purple line here is the spectrum that we've obtained from SIM and solstice for a quiescent period. And the black line is a theoretical model. And we have to do this because that region of the spectrum has never been measured. And the integral of this spectrum is 1360.45, which is the new quiescent background solar radiance measured by SORCE TIM. The green lines are just theoretical Planck curves that are looking at, you can essentially say if you theorize or approximate the sun as a black body, you can roughly see that it has a temperature of roughly 6,000 Kelvin, and different black body curves here show that as the temperature rises, the peak wavelength goes slightly to shorter wavelengths. So I'm going to skip this and just look into some comparisons actually. So how well can we model the total solar radiance? In each of these panels, the model is in green, and the gray is the uncertainties around the model, and the purple dots are the SORCE TIM measurements. This is a high activity period, and this is over solar minimum, so minimum activity. The gray uncertainty bars here don't actually include the uncertainty in the absolute uncertainty in the measurements. And this is actually over the whole period of record for SORCE TIM. So we're modeling it typically within 0.5 watts per square meter. And we're doing the same thing with the spectral radiance. I'm just showing a couple results here. Integrated over a couple broad wavelength bands in the UV and the near infrared. Again, the model is in the pink with the gray uncertainty bars, and the green is the measurements. And the improved accuracies and long-term stabilities of the future instruments will help us improve these comparisons more. And our biggest thing that we want to say about that is our ability to model the sun today allows us to predict or model periods long ago. And so we can learn things about the sun even when we didn't have measurements from space. So I bring up as one example, here's Galileo showing his telescope to the Venetian Senate. I learned he actually didn't make the telescope. He didn't design it. A guy named Hans Lippershey designed it. But Galileo made his very own without seeing it ever the next year and then pointed it at the sun. And then we have our longest climate data record ever is in the sunspot numbers, and go back to about 1610. And there was a period here during the Maunder minimum where the sun was very prolonged quiescent period. So our question is, if we can understand our solar radiance today, then we can look and see what impact did the sun have on Earth's climate if we were back at a time when it was a really low quiescent period. So we have a better handle if the sun was to do this again today, what would be our impact on our current climate? And these are some examples of groups that have tried to look at this. So these are different representations of model TSI back in time, different studies, envelopes of, the gray bars are just envelopes of what they're seeing there. So larger uncertainties yet. So let's look at the future. And I've really largely set the stage for TSIS by going through what we know currently. I've already talked about lots of what's going to happen with TSIS and why. So I'm really talking here, going to mainly talk about what are the advances in the measurements of solar spectral radiance, similar to what we've achieved for the total radiance during the SORCE mission. These are the TSIS TIM instrument and the TSIS SIM. And there's Eric Richard back there. Mason, that's your dad. Skipped here. So lessons learned. TSIS SIM shares the same name as SORCE SIM, but there's more than a couple differences, but two that I'm going to focus on. TSIS SIM has an additional channel, and due to the development of a spectral spectral radiometer facility similar to the TSI radiometer facility, we have much improved absolute accuracy calibrations for a pre-launch period. So similarly to the TSI TRF, the spectral radiometer facility has a cryogenic radiometer for the standard for radiance, and it has, say, a SIM instrument and a vacuum chamber. What's different is the beam optics come, and they come in through here, and there's a turning mirror that can push the laser beam this way or this way, same focal path length between the two, and same vacuum window where it's coming through. Those common to both things. So what we're able to do is compare radiance measurements from the cryogenic radiometer to those from the instrument under different polarizations of light. The sun is unpolarized, but we can average our different polarizations to get a representation of unpolarized light. And here is what it looks like, the sausage making radiometer. Here's the SIM instrument in there. What I want to show here is, while this plot may not look the most exciting, it's really a Herculean effort. The calibration and characterization approach for the SIM instruments are such that they follow a measurement equation approach, which means that this is our measurement equation. There's power, area of the slit, absorptivity, transmission of the prism, diffraction, slit function. If every one of these elements is calibrated and characterized. Then we look at it in this end-to-end validation with this TSI radiometer. If we understood the instrument perfectly, there would be zero difference between the result in the radiometer, cryogenic radiometer, and our measured result from the instrument. And you can see that there's this variation of curves here, but within 0.2% absolute accuracy is what we've achieved through this SRF facility. So very Herculean effort. Actually was said that we couldn't do it. And I see that I'm getting short on time. So I'm going to, if it's all right with you, Eric, I'm going to maybe not talk about the long-term stability that we're doing. Let me say it this in words. We have, with the addition of the third channel, how this works is if you're measuring the sun and your instrument is exposed to harsh solar radiation, the optics degrade. So your measured signal decreases. And you want to separate that instrument signal from the variability of the sun. So you have another channel, you turn that other channel on, and you make comparisons from the more pristine channel and the often used channel. What you can then determine is over a period of time where your often used channel has developed a lot of exposure time, so it's spread out along this exposure curve. The less often used channel is clustered up in here. And you can fit a curve to this and then measure as a function of time what is your decay rate on your often used channel, and you can correct for that. So what I'm showing here on the bottom right is with how well can we correct for long-term degradation? What does a third channel give you? And this is a modeling study here. If you just focus on the green line on the bottom, if we then have a third channel that we only open up once every like 200 days, by the end of the mission life, it's still pristine to within our uncertainty bars. So even if our often used channel and our less often used channel have both degraded, as they're showing here, past our requirements, we can turn on our pristine channel and just correct for that. So that's where our long-term stability comes from. So that is TSIS, and I'm skipping to some fun stuff here. So we are going to go to the International Space Station. So this is a new challenge, and it's very exciting. And some of the technical engineering challenges are contamination. The International Space Station is a large structure, and people are worried about, well, it's going to give off gases and particles and stuff. It's going to damage our optics, and the data isn't going to be good. And they have particle counters on here, and they've demonstrated with other instruments that we don't think this is a problem. And so I'm not going to talk about that. What I wanted to show is just some engineering movies in my last little bit of time here, showing how we achieve our solar viewing time. How can we view the sun from this structure when its solar panels are going around and it's got all these wiggles here? How do we get an unobstructed view of the sun? How do we track the sun? How do we handle the disturbance of a space station as it kind of wobbles and goes around in time? And how do we maintain our pointing? So lots of words here. Biggest thing that I'm going to be showing, of course, here's the TIM instrument. Here's a SIM, just so you have your perspective. Some fine sun sensors to target the sun. And there's this platform has a 2-axis gimbal, and new to it is this 3rd-axis deployment system. This bottom part here, the FRAM, I forget what that is called, but that's provided by the International Space Station. We have to mount our optics bench and instruments and the 3rd-axis deployment system to that. It's all integrated at one time to the International Space Station. So let's take a look here, because a picture is worth 1,000 words. Here is, so let me just see. These bolts are one-time use. They're basic, so when the instrument goes up in the launch vehicle, it doesn't shake loose. So here they're coming out. There's the gimbal system. There's the 3rd-axis deployment system moving the arm. So it gets away, it gets high. It's going to allow it to get up above the structures of the International Space Station. This is the latch for that arm. And now it's just going to be showing the really broad range of motion. As I understand it, it has to, because we need to measure the sun every orbit, and because of seasonal variability, where the sun is low on the horizon or high on the horizon, we have to have a lot of motion in our gimbal system to be able to achieve our solar viewing time under all these considerations. And the other thing is that with that 3rd-axis deployment arm, we also have to be able to move it back in, because anytime there's an astronaut out in the space station, it has to be brought back in and stowed for safety reasons. So this is another fun one. This is TSIS is tracking the sun. Well, it's an engineering movie. Well, it's on a space station, so it's a one there. Oh, wait. I thought this was an engineering movie. What? I think I'm, oh my God. Just kidding, April Fools. So yeah, that was gravity. How'd that get in there, Pat? I don't know. All right, so here, let me see. So this beam of, so this is right in this region is where the TSIS instruments are, of about 15 orbits a day. You can see as it's looking, the space station it's really moving in all pitch, roll, yaw directions, but the yaw is really probably more exaggerated in this engineering movie than it is on reality. But and then I wanted to show, there's a way to show it better than in that movie, but we'll get back to this third axis deployment system where how the TSIS instruments are essentially, when they're mounted to the International Space Stations, how do you get your instrument high enough so it's not obstructed by the structure of the International Space Station. So also wanted to say we're going to be riding on the Dragon trunk, SpaceX Dragon trunk, which I'm actually really super excited about. I'm not sure why. It just seems cool, I guess. This is it here. This is an artist rendition, but it's showing a robotic arm. I think this, I could be saying this wrong, but this little contraption at the end is called Dexter, and he's connecting the Dragon to the International Space Station. And just because this picture just isn't enough of a word, I wanted to show an actual movie. This is not an engineering drawing, it's an actual movie of the RapidScat instrument that was launched and instrumented on the International Space Station late last year. And it's a follow-on to QuickScat, which is the, QuickScat was operated here at LASP, Mission Ops, and RapidScat is also monitoring the ocean wind, so it's like hurricane monitoring. So this is super cool, and I'm sorry it's 8:30. I'm really essentially very near the end of the talk. So here you can see I always have to think about, turning myself upside down. I'm hanging like a bat from the ceiling. You see the earth underneath you. So there's the robotic arm coming in to the Dragon trunk. It's lifting the RapidScat instrument out of there. RapidScat, this right there is the FRAM that the International Space Station provides. Everything's instrument on there. It's now carrying it over to where it's going to be docking it. See here, it's going in just like a Lego piece. Click.
Power cords are in there too?
Power cords? So the power cords are to...
That's 8.3 of the activation.
Yes.
And the
Sorry.
And the telemetry?
Yeah.
All the electrical connections
That has been issued.
So this is going to be us in 2017 when TSIS goes. We'll be all nervous. They're clapping because it wasn't just enough to get the instrument there. They needed to see it work. See, now it's turning. So finally, the scientists and engineers saying, now we did it. Job well done. So that's that. And so just to reiterate, I wanted to show this picture again. So here, you can see this dot right down here. This is actually engineering drawing of TSIS connected to the external logistics carrier, I guess ELC. You can see the third axis deployment arm there. It can basically lift the instruments. Here's Tim. You don't really recognize Tim here because in this drawing it's gray, but you saw those pictures before. It's really gold, like Tim, but I guess it's the forgotten child here. Anyways, there it is. And so it's going to be lifted up and above and has its mobility from there. And just one last photo. This is the future home of TSIS right here. Just I pointed out some other things that I think I got these right. Japanese module, the Columbus module, Destiny Lab. This is where, if you've seen the astronauts taking photos of the Earth, it's got the windows to the exterior, so they have the view of Earth from here at Destiny Lab. This is the Russian module. And the astronauts really, I guess they just sleep wherever it's convenient, and they eat wherever it's convenient, but they do have a galley here and here. But anyways, that's kind of that. And if someone did want to watch one more movie, that'll be 1 more minute of your time. I have one more I could show, but I will stop because I know I've taken a whole hour. So thank you for your time, and if you have any questions or if you'd like me to show the other movie, I can. Show it? Okay. All right, I got it. So this is engineering developed movie, but so showing the robotic arm, it's pulling this Opal's instrument out of the Dragon trunk. I mean, it's just fascinating. So watch what it does here in a bit. So it's got a little workbench. So he sets it on his workbench for a while, and then he says, oh, I need to position myself differently. So he drops his dexter, the arm moves, it walks over to another part of the station, and then picks up dexter on the other side. So now it's going to go back and pick up the instrument from the workbench, and now it's taking it over, and it clicks it into spot. Click. There. Easy peasy. So, anyways, just fascinating, isn't it? So, yeah. All right.
When you said like Lego, and when it sticks in there, is it little detents or what holds it in?
Pat, do you want to answer? Because I've not actually seen that part, but they have the FRAM in the here, and they're building to that. And to me, it looks like it has these indents and connecting sort of click. But Pat, do you know better?
Yeah, there's a bolt on the end of the pallet, and that bolt drives a mechanism that puts two rods that insert into corresponding slots on the base piece. It just sort of drives it like this. And so the robot arm turns that bolt, moves that mechanism in, and then in addition to that, there are magnets that help to remove any slot removal.
Oh, I'm not sure. What? Yeah.
So is the robot pre-programmed, or is this under astronaut control? Fully autonomous?
It's controlled from the ground.
So they can block it.
Yes, the astronauts actually don't control the arm during any of that activity. It's all drummed up the Space Flight Center. And so, by the way, in August of 2017, we'll launch. About a week later, we'll start going through that activity. And I'm sure we'll have a big party
Yes.
where it'll be projected, and you can come and actually, unlike most space deployments, we'll actually be able to watch those activities in real time. And once we get installed, we'll actually be able to see our instrument operating in space. The deployment of that third axis system, the testing of it, it will be amazing. So,
Wow, when is that going to be?
well, the launch is August 2017. It takes a week potentially for it to move from the Dragon onto the pallet, and then probably another week. But we'll schedule all of that and announce it so that it'll be open to the public.
Amazing.
Very
And
exciting.
maybe I was the only one surprised. I didn't realize that the robotic arm could walk anywhere on the space station. I thought it was kind of situated, but it
Those solar panels at the space station, they were spinning. Do those spin all the time? Just go.
Check the sun. Those continue. Once in a while they stop, they pause them. If they haven't, they need to do some kind of orbit maneuver. They can pause them and they can off point them to the sun to reduce power. But most of the time they just track continually track the sun as it goes around.
How often does that get to your field of view?
It's,
So it's very complicated. Pat's done an extensive analysis.
Yeah, I think we get about 10 days per year when the TIB instrument has a wider field of view that you want to keep all sources of light out of it. And so about 10 days per year, the light, the solar panels will block some of the light from the sun. And you won't get those things. But the SIM instrument should be able to keep getting data during those times. So we're designed to be able to operate over all of the angles at which the sun moves in the sky.
We have a World War I interrupter gear on there, just like colors are shooting
yeah.
1910 technology.
Well, it's pretty amazing.
Isn't it? You know, and I didn't really so this third axis deployment system, I was talking with Pat and other instruments have had this, but this is really a new ground that they've done here because they have to be able to do this tracking the sun to these large degrees every orbit. And so the motions and the motions under which this third axis deployment system has to work is larger than what they're experiencing than other instruments have had to do. Did I explain that right?
Plus, it's amazing that this thing is flying through space and,
It's not there.
well, I mean, that you can move around. I mean, I think about walking across the living room floor and I'm lucky to get to the door.
It is amazing.
Yeah.
It's actually really inspiring, and for some reason, just the fact that to me, the fact that the instruments are going up in a trunk, I don't know, it's kind of both futuristic but also very antiquated at the same time. So
How do they pop the bottom off of that?
It's open. When it separates from the launch vehicle,
It's
it's
open.
just open.
so that the arm just
It's a cup.
can reach right in there.
Oh.
That's why it's called the trunk.
Now that we have the satellite measurements over a period of time, is there a way to correlate with terrestrial measurements that have been going on maybe for 100 years? Are there instruments that have been operating a long time?
Right now we have surface temperature records. We have lots of Earth climate data records.
Any solar radiation measurements?
We do have surface measurements, of course, of solar radiation, but they've all largely impacted by the atmosphere and the clouds. So it's not solar radiation at the top of the atmosphere; it's at the surface.
Right.
Trying to ascertain to connect
Right.
these two together to close this is very challenging, and
Is it?
but these sort of studies, these correlation studies, have already been going on. They'll get better as our individual instrument records get better. But so, for example, we already have a basic understanding that the sun, if you look at the instrument records of solar radiance and absorbing gases in the atmosphere, surface temperature, and the volcano records, just with those components alone, you can account for much of the variability in the surface temperature. So we have an idea of what degree the sun impacts Earth's climate. Where they're really getting to in terms of how does this dispensation of the spectral energy in the atmosphere, that's actually just something that's really taking off in this decade and into the future. And so there might be certainly some compelling studies that are seeing more regional effects between the sun and oscillations in the ocean and causing increased precipitation in certain areas. So these sort of studies are...
I was thinking more like Walter Roberts was up at Fremont Pass with his solar observations in the Second World War, and I thought that went on for quite a while.
Maybe, I
And I was wondering
don't know.
if there was a way to kind of work a correlation to use those records as part of a continuous.
And so,
Just asking.
right, I don't know the answer to that, actually. Yeah.
Why put the instrument on the space station? Why not a separate satellite which would seem to have less interference?
Yeah. Well, it wasn't our first choice.
Go with the state.
I'm laughing a little bit because I skipped over that. This was this slide with all the words. There's quite a long history to TSIS, and so you can look back in 1998 and to where we are now. I think we've had more than our fair share of programmatic sort of interruptions, if you would want to call them that. So TSIS was selected for different satellite systems, the NPOS, and then JPSS. For a while there, it was assigned to a polar free flyer, but through funding challenges, this is the scenario where we are now. So we have go through here a little bit more systematically. So, oopsie. This NPOS was a really large conglomeration. I don't know of a better word right now. Yeah, and it went over budget, like significantly. So there was this thing called the Nunn-McCurdy review that said, we'll shut you down. We've shut you down. You're costing the taxpayer too much money. You haven't done what you promised. But then there was this big hoopla, of course, because the total solar radiance is a critical climate data record. And there was other, I think there was an energy instrument to measure Earth-reflected radiation in, I believe it was in the thermal. I might have that wrong. Anyway, so there was these NRC workshops. So kind of leading scientists in the community got together, said we need to continue these records. So there was pressure to continue them. So then we went from NPOS to another large conglomeration here, which was now two large agencies as well. So NOAA and NASA had the Joint Polar Satellite System. And there was this free flyer division of this JPSS, but it wasn't funded. And at the same time, our Glory TIM, which failed to reach orbit because of the launch vehicle failure, put actually even additional stress on the scientific community to continue this record of total solar radiance. And so they did, I guess, establish a different polar free flyer, and it was going to have the TSIS instruments on it. And the SARSat was a search and rescue satellite, so if someone falls off a boat in the middle of the ocean, they can activate their emergency beacon and someone can go find them. And then ADCM was like I can't quite, it's advanced data collection of some sort. It's for environmental variables. So they established this polar free flyer, and then, but it, things were obviously not going smoothly. So here at LASP, they had this concept. They conceived the TSI calibration transfer experiment using the SORCE TIM witness unit. And here the engineers at LASP we were able to get on this STP-SAT-3, which was a ball-built satellite, and whoosh, up we go. So we're making the measurements, and suddenly there's a little bit less stress on maintaining the TSI record, but not completely, because the TCTE was only making measurements once a week or something like that. It was this low cadence. So then we were able to show that we actually weren't catching really important solar variability. So we've since been able to, we've been allowed more viewing time. So we are getting more frequent timely measurements from TCTE. But the issue with TCTE, or not the issue, but it's the SORCE TIM instrument, not the Glory TIM, which was the more advanced and high accurate. So we have a TSI measurement up there, but still not the high accuracy we really want for climate studies. And then finally, this polar free flyer was separated from the JPSS program. We launched TCTE. That polar free flyer was not funded, and something called SIDAR was created, which is the Solar Irradiance Data and Rescue. Now, so everything has an acronym. And so it's a new acronym, but the same instruments. And as part of this, the impetus to implement on the International Space Station came about. So this is obviously, was not our first choice. It's kind of a series of events. I don't know how better to quantify them. We're scheduled to deploy in 2017. The engineers are hard at work implementing the instruments for deployment to the International Space Station, and currently we're funded. so.
One quick point to that, Tom and Pat could probably chime in, but it wasn't always the case that the ISS was going to work for the solar instruments, particularly when the shuttle was going to it all the time. Whereas one of the critical things with these instruments, since they stare at the sun, is contamination. You have contamination on your optics, you'll degrade a lot faster than we planned. And so I think now, since the shuttle is no longer going to the space station or in existence, the contamination environment is more manageable for
Yeah. There was this one, there was a RAIDS instrument.
Well,
And
Tom can chime in on that a
yeah.
bit more.
I didn't bring all this other information in, but there is a radiation measuring instrument that was deployed on the International Space Station in 2009, and they haven't had any significant impact to their sensor measurements. And then I think I did mention that there is some sort of particle monitoring as part of the, I guess, the housekeeping of the International Space Station, and they're meeting these particular requirements. I'm not sure how that compares to other environments, but.
In your pictures of the sunspots over a significant period, you had the models as well. So what are the inputs to those models? Is it just number of sunspots?
So there's different models. The model that we're working with here that comes from Judith Lena at the Naval Research Lab, that's a proxy model. So yeah, that's a very good question. We assume that it's only two things that change the sun from background conditions. It's sunspot darkening and facular brightening. So those are the only two things that we consider in that model. And so how we use proxy inputs for that. For the sunspots, we use a record of the sunspot area and the location. And then for the facular brightening, we're using the magnesium-2 index, which is a solar emission line indicated of chromospheric variability. So it tracks very highly with the solar variability. So as there's more and more active regions from these magnetic features, they pop up into the chromosphere, and we're measuring that in the magnesium-2 line. Thank you. I've really kept you late.